Okay, welcome. Thank you. All right. So a couple of things I wanted to point out. I was looking at our schedule. Well, one, I realized now that I put it in student mode, the rest of the school year is hidden after reading break. It's like, oh yeah, we'll figure it out. I'll unhide those. I don't know how I forgot that. Sorry about that. It's a surprise. No, we're just gonna keep working through the textbook. But sorry about that. But you have to click on this little hedgehog, but it'll start spinning. I was hoping it would be faster than that. But anyways, little cutie. It used to just spin on the page, but I don't know, it doesn't do that anymore. One thing that I was looking at though is, now let's see here, is this kind of, I'll include that the following week is reading break because that's kind of the pressing issue here. So today we're gonna finish conditional probability from last day. So we're just a smidge behind, but don't worry, I have these secret buffers built in. When I say brief, it means we're not doing them. We're gonna say we did them. They're not on any final exam or test or anything. So yeah, we did them so briefly, you didn't even hear me talk about them. So brief. In our case, I'm tempted to also make 3.4 brief. So what I want to do is I actually want to finish conditional probability. So here, I'll add that this one will be brief as well.
That's just because you don't like this chapter.
I hate this chapter. Well, so part of the reason I don't like it is because it's overly kind of complicated, and if we had a whole term to spend in it, sure, but we don't build on it later. It doesn't. So we do all this hard work and we figure out all these hard things, and then we don't really need it later anyways. So that's my beef with chapter 3. They're good to know things, and they're things we have to do, but here instead we're going to continue conditional probability because that is important. And we're going to start 4.1, which is the normal distribution, which we were supposed to start to kind of plan start on Thursday, but I'm going to get a head start. Now for that reason, and part of the reason I want to do that is because I do feel bad about putting a quiz on the Friday before reading break. I don't know if you had plans to take off, but I certainly would have if I was a student, catching that Greyhound bus, going anywhere but here. I don't know. So one thing I want to kind of suggest, gauge, is if you would prefer to have the quiz on the Thursday instead.
Some of us have a test right before
On
the quiz would be like at 11 o'clock.
Oh, the Thursday?
No, on Friday.
Oh, on the Friday?
We've got a test at 11, and this class right after. So I don't know.
Oh, well, that sounds terrible. Would it be better switch to Thursday? Just if anyone,
Sorry.
yeah.
Sorry.
Oh, hello.
I won't be available on Thursday.
Oh, say that again, sorry.
I won't be available on Thursday. So I
Oh, you're not available on Thursday?
yeah.
Okay. I've got a solution for that, I guess. All right. because you could just write it on the Friday when you were supposed to write it. I don't know. I just don't want you to have a pile up on the Friday either. Okay. I am tempted to move it to the Thursday because it sounds like it would be generally better. Okay. But if that's a problem, then you reach out to me and we'll figure something out. I'll just have 2 different quizzes or something. This stuff, I've got so many different copies of stuff. Thursday, quiz number 2. See me. You don't have to physically see me, but talk to me if that doesn't work, right? If see me if you want to write, oh, oops, eraser. If you prefer to write on Friday. Okay. Because I don't like to move quiz dates, but I also don't like to have them right before our only break. It just worked out that way. So one of the things that I will mention is the binomial distribution is on the quiz, but I don't quiz the geometric, the negative binomial, and the Poisson. We just need to talk about them, but I'm not going to quiz them. They're not on the final exam or anything like that. Okay, so quiz number 2, it goes.
Sorry, Emily, one more question. The Thursday is not this. Sorry, Emily, one more question. The Thursday is not this week, but the
No,
other
not
week.
this Thursday, next
But
Thursday,
the other week. Okay.
because we're
then
here.
Okay, then that's fine.
Okay,
That's
Cool.
fine. Thank you.
no worries.
Thank you.
Okay, so it's just up to 4.3. And then my plan is that if we have the quiz on the Thursday, then I'll just post the no class. I will talk about these 3 distributions that are nice to know about, right? But like I said, they're not being tested or anything. So you'll have an assignment on them, but I'll do that on the Friday. So if you're busy or whatever, you can just watch the recording after, and it's not a big deal. Okay.
Is it still going to be 15 minutes, or are we gonna work on
The quiz on Thursday.
Yeah.
Well, I might take advantage and use the full hour and 20, make an hour and 20 quiz. I mean, it's not going to be that different, but hey, it's working out. Yeah, it'll be the whole class though, that you'll have to write it. Yeah. Yeah. It just might be a little fast or something. That's all right. And then, so then the move would be Friday, 4.2, 4.3, and, oh, sorry, 4.4. Makes you wonder, oh. Okay, not 4.2. Gets confusing. Oops, sorry. 4.2, 4.4, and 4.5. Those are kind of flyover sections, if that makes sense. So basically 4.1 and 4.3, they're the money makers. Everything else is just extra. Okay. Okay, yes.
Is it gonna be cumulative? Or just-
No, just so everything after quiz 1. Yeah. Can't remember what chapters, quiz 1 was chapter 1 and 2. Quiz 2 is chapters 3 and 4. So probability and these distributions that we're going to talk about. Okay. So like I said, a little bit confusing, I guess, but we'll see if we can start the binomial on Friday, maybe. Usually it takes me a while to get through the normal distribution. Okay. A little bit of review here, or continuing from Friday. Wow. I wouldn't blame you if you forgot that I gave you something to do on Friday. Continuing from Friday, we were looking at the smallpox data set, and we said this much so far. Sure. So I basically just ran through and gave you some notation to use, but let's just reread the question. So consider the smallpox data set, which was from the 1700s, I think it was, in Boston, where they were inoculating people for smallpox. And so suppose we're given only two pieces of information, okay? 96.08% of residents were not inoculated, okay? And so then, well, I guess I should finish reading it. And 85.88% of the residents who were not inoculated ended up surviving. Okay. How could we compute the probability that a resident was not inoculated and lived? Okay. So we identified two events, right? Someone's either inoculated or not inoculated, and then we wait and see, and they either survived from they survived smallpox, or they did not survive smallpox. And so we use some notation to denote these two events. So I is for inoculated and S is for survive, which means that the complement of I is everyone who's not inoculated, and the complement of S is everyone who did not survive, which means that they died, right? But in terms of the complement, right, it often makes more sense to say not survived, even though that's not nice to read, right? But just in terms of the inoculated and the survival. Okay. So here, all right, let's list the probabilities that were given with proper probability notation using this these shorthands. So we know that 96.08% of residents were not inoculated. So we know the probability of not inoculated is 0.9608. Thank you. Remember, we usually report probabilities in percentages, but then as soon as we're doing math, you should convert them to decimals, right? So proportions. Okay. So then the second piece of information we have is that 85.88% of the residents who were not inoculated ended up surviving. Now, this is going to be a conditional probability, right? Because we know that they're not inoculated. So then what's the probability of surviving? So then the probability of surviving, given that they were not inoculated, right? So kind of sneaky, right? This here is a conditional probability. Okay. So you want to spend a little bit of time working out that notation, right? And so when it says of the residents who were not inoculated, then you know that out of, so they had to be not inoculated, right? And then there's some probability of surviving. Okay? And so that probability is 0.8588, which so now we have this information. Now we can start thinking about, okay, what do I need to solve here? So how can we compute the probability that a resident was not inoculated and lived? Okay. So here, what we want to find, the probability that they were not inoculated and lived, so and survived. When we have this and in here, right, that's when we can use the multiplication rule. Okay. And so here, if we recall, the probability of A given B, or rather, sorry, A and B, I'll use the rewritten version, which we rearrange and on blast day. The probability of A and B is the probability of A given B times the probability of B. It could, yeah.
And these are like formulas that we'll have on our.
Yeah. Or it could be the probability of B given A times the probability of A, right? It doesn't actually matter. Because we don't know from A and B, we don't know which one happened first, but obviously the one that happened first is the given part, and that's the probability that you multiply by on the end. Okay, so I want to find this guy here. So I'm going to write that out beneath the general formula, and then I'm going to map that general formula, right, to the components that I have, right? So now I need to keep track of, okay, the person is either inoculated or not inoculated, right? That's the first thing that has to happen, right? In order for them to either survive or not survive from smallpox, right? You're not going to inoculate dead people. It doesn't make sense, right? And so first the inoculation has to happen, and then surviving or not surviving has to happen. So in this case, right, the second component here has to be the inoculation, right? The first step. So given that they were not inoculated, right, what's the probability of surviving? Okay. And so here, I'm going to write out, we want to find the probability. And this is where I'm going to get sneaky. S and not inoculated. Why did I switch them? To make them match that formula, right? Not I and S is the same as S and not I, but because I had to happen first in order to match this first formula here, I'm going to have the probability of S given not inoculated times the probability of not inoculated when I map that out. Okay, so it does take a little bit of kind of fine tuning, tweaking, but just remember that the inoculation had to happen first. So that's the given component. It also helps kind of put you on the right track with the information that you're given, right? There's not much else we can do here, right? But multiply these two together. Okay. And so now I have 0.8588 times the probability of not inoculated, which is 0.9608. Let's see if I have something here. 0.825135504. Hopefully that is correct. I'm just following it blindly. So that's looking pretty good. right? Why do I say that? Because the probability of surviving and when you're not inoculated, right, overall is 82.5%, right, or 0.825. So pretty high. Yeah. Usually when we have these kind of conditional events, right? So event 1 has to happen first and then event 2 has to happen. It helps to organize that information in a tree diagram. Or even if you're just talking about event 1, event 2, event 3, maybe they don't have to happen in order, right? But when you have these kind of probabilities that follow one another, a tree diagram can be really useful. Now, I am going to make you create a tree diagram on the quiz, of course, and then I'm going to get you to use it to solve problems. So buckle up. Okay, I'll say that's the end of the review from last day. To help us organize information for probability questions. Like I said, you can use them for probability questions, but usually conditional probabilities. So to help us organize information for probability questions, I'm going to say especially conditional or consecutive events. We often use a tree diagram. So a tree diagram is going to look, and I'm just going to draw it and erase it, and then we'll draw a nicer looking one, but it helps to know what it looks like. Okay, so it might look something like this. Right, so here I have my first set of possible outcomes, right? So my first event that happens, right? A, B, or C are the outcomes here, right? And then the second set of things that can happen is one of 2 events, okay? Or one of 2 outcomes, I guess. Okay, so for example, here, if I have, well, like I said, I'm going to erase this one. I'll make a really nasty one. Usually I don't do this, but if I roll a die, right, then I have a 6-sided die. And I was just bragging that the internet had been fine for me to Zoom from here. And then now it clinked out. Let's see here. But I think it keeps recording, so I guess. All right, here we go. Totally lost my train of thought. Oh yeah, so first thing I'm gonna do is I'm gonna roll a die. It can be one of 6 things, and so I'm gonna just sketch 1, 2, 3, 4, 5, 6. All right. Each possible outcome, only one of those is going to happen, right? But if I want all the possible outcomes, and then I flip a coin, which has 2 possible outcomes, right? So at the end of each of these branches, I have two possible outcomes. Okay. So here, this is the first event, and this is the second event. But notice that the second event happens off of each branch. Right? You only head down one branch. Okay, so like I said, I am going to erase this because that's gross, and I'm going to include that information on our nice looking one, okay? But not so crazy and overwhelming like that first one. If we take the inoculation information, for example, right? And so let's consider the smallpox example. We decided that the first thing that has to happen is, were they inoculated or no? Okay. And so here at this first set of branches, so this one I'm going to keep, so I'm going to try to make it nice and clean here. This first set of branches is, was the person inoculated or not? And so what I'm going to do is I'm going to denote it by a little I on the, it doesn't matter which branch you put it on, right? But on one of the branches, and then they were not inoculated on the other branch. Okay, so at this level, okay, the first event were they inoculated? A single person only heads down one of those branches, right? You either are or you aren't, but it doesn't matter, because after that, right, the second thing that can happen is you either survive smallpox or you don't, right? So the next thing that has to happen is, and maybe I need to give myself right. So now, if they were inoculated, right, they either survived or they didn't. If they were not inoculated, right, they either survived or they didn't. So that's the second event, right? Did that person survive? What happens when you read branches, right? If you've gone down this branch, you end up with a person that was inoculated and survived, right? So here, this is a person, let's see here. I and S. Okay. If I go down to this kind of next set of branches, right? So it is a tree diagram. We call them branches, of course. And so this is a person that was inoculated and did not survive. So I and not S. Next, someone who is not inoculated and survived. So they were not inoculated and survived. And then finally, I think you get the idea, not inoculated and did not survive. What I do, because I get lazy, is I stop writing the and, but I do like to have the reminder at the end of each branch what the combination is. Okay, and so here you could write, or I just write IS, I not S, I not, or sorry, not IS and not I, not S. Okay.
Is two then need to be consequences of each other, like the second is supposed to be the consequences of first, or it's not?
Do you mean when I write it like this?
When you put the tree diagrams,
This has to be the first thing that happens.
because you mentioned earlier about example, roll the dice and flip the coin. It's
Yeah.
like the consequences of each other, but this, I mean, survive is the consequences of, you know.
Yeah, so it's the difference between, so here we have conditional probabilities or conditional events, right? And so the probabilities, I should do it on here. The probability of surviving, right, depends on whether they were inoculated or not. But you can also do it for independent events, right? So if I roll a 6, that doesn't change the probability of flipping ahead, right? But you can still draw it out and you can still use the probabilities in the tree. But they just wouldn't change across the branches. Whereas here, right, the probability of surviving, given that they were inoculated, is going to be different than the probability of surviving, given that they were not inoculated, right? Okay, I think we're ready for putting the probabilities on this tree. Okay. So now what you're going to have is underneath each of the events or outcomes, you're also going to have the probabilities, right, associated with each outcome. And so we'll start off nice and easy here, right? The probability of I and the probability of not I. Those are just pure probabilities, right? You're either inoculated or not. However, if I head down this branch, right, this becomes a conditional probability, right? So the probability under S, right, given that I headed down the I branch, so this probability that I would write here is the probability of S given I. Same thing, right, for the next branch over. The probability that I need to write under this branch or under the not S is the probability of not S given that they went down the I branch. Okay. And you'll see why this is so important in maybe right now, right? I'm going to fill in the rest of this tree, but just to show you why it's so important that we do this is because now what we can do is you can multiply down a branch, okay, and read it as I and S, right? And so you can use these probabilities and say that the probability of I and S is the probability of I times the probability of S given I. Notice I'm just multiplying down the branches. You can rearrange this, right? You can put the probability of I on the end, and all of a sudden you have the probability of I and S, or S and I if you prefer. Okay. And so we can multiply down the branches to find the and probabilities. So that means that, okay, then to get the probability of I and not S, right, I multiply down the branch that made that happen, right? And so I get the probability of, let's see here, can I do it like this? The probability of I and not S is the probability of I times the probability of not S given I. I'm running out of space here, so I should do it for all of them, but I'll finish up the branches here. The probabilities under these branches would be the probability of S given not I, and the probability of not S given not I. So we have these conditional probabilities, but conditional probabilities, right? If the probability of surviving did not depend on whether they were inoculated or not, right? For example, flipping a coin, it doesn't care what you rolled for your dice, right? And so then that probability would just stay the same, right? But in this case, we have these conditional probabilities, and that's usually when we're using the tree. Okay. So, all right, I'm gonna see if I can, I'll do a little weaving here. The probability of not I and S is the probability of not I times the probability of S given not I. And then finally, the last one, probability of not I and not S is the probability of not I times the probability of not S given not I. One thing that you should check, right, is, okay, let's take it back to our roots. At the end of all these, I and S, I and not S, not I and S, not I and not S, is what? That's our sample space. Those are all the possible outcomes. There's nothing else that can happen, right? And so what we need is we need the probabilities at the bottom of all these to add to 1, right? And so notice here, let's use a different color. A lot of arrows to follow here. Wah! If I had a bigger sheet, I would just fill the bigger sheet and it would still be a mess, I think. But anyways, kind of limited here. All right. So I guess I could do it on the board, but then it's gone forever. I don't like that. Yeah. Oh, sorry. It's gone. So notice maybe these instead. These outcomes make up the sample space right? All possible outcomes. So the probabilities must add to 1. Huh? Do we have enough? We don't know the probability. We don't have quite all the information that we need to fill in the entire tree. Okay. I guess I could find it, but instead of kind of beating this example to death, how about we use a different example? Okay. But before we do, what if I just wanted to know what's the probability of surviving? So now I don't care whether they were inoculated or not. Now I just want to know, okay, what's the probability of surviving? What's the probability of S? Right? And so what we need to notice is that, okay, well, S happens down this branch, right? Or, remember when we say or, we're adding, right? So, or when I head down this branch, right? So it's either I and S or not I and S. Okay? And so you can use these branches to find the and probabilities at the end, but usually we work them a little bit more and say, okay, then what's the probability of surviving, right? What's another thing? What's the probability of someone who is not inoculated nor surviving? It's kind of a weird example. I basically want the complement of this first one. How would you do that? I would leverage the fact that these all add up to 1 and subtract the one I don't want, right? And that's going to be the same as taking the second branch plus the third branch plus the fourth branch, right? But it's a little bit quicker. Okay? So I have a better example where it's easier to talk about. Okay? But just as an example here, right? Just what is the probability of surviving? So the probability of surviving is going to be the probability of I and S plus the probability of not I and S. And here, the plus, you read it as or. All right. Let's do a proper example here. 3.43. Oh, so here they have the tree, they put it on its side because it prints nicer that way. I always find that for me, I like to work from top to bottom. It doesn't matter if you write it on its side, you can. In our question, all we were given was the probability of not being inoculated, right? Which means that we could easily find the probability of being inoculated, right? 1 minus this. So far we had those key pieces, okay? But the only thing that we were given was this probability, I think, right? The probability of someone surviving given that they were not inoculated. So we could find this probability, right? Because these branches have to add to 1, these probabilities together, right? Because they're all coming down from this first branch. Okay? And so I can find the probability of not surviving given that they were not inoculated, but I can't, with the information, the limited information that we were given, we weren't able to find these values. But here they are, and you can work them out. Yeah. But I have 3.43 is the one I want. Technically, what we are using is Bayes' theorem, but I'm not going to call it that because it just makes it more confusing, in my opinion. It's this huge formula, but I just want you to know that you can solve these problems without using Bayes' theorem technically. Okay. All right.
Sorry, what was the little column?
Oh, it's, I've written a poor version of or,
Oh,
right? So as soon as you're saying or, then you're adding. When you're saying and, then you're multiplying, right? Okay. Jose visits campus every Thursday evening. However, some days the parking garage is full, often due to college events. Hey, sounds familiar. I was circling for so long today. And I was tempted to go park at the church, but I'm too lazy. I was like, one will come up. I just know it will. There are academic events on 35% of evenings, sporting events on 20% of evenings, and no events on 45% of evenings. When there is an academic event, sounds like a conditional probability to me, right? The garage fills up about 25% of the time. Okay? And it fills up 70% of evenings with sporting events. On evenings when there are no events, it only fills up about 5% of the time. If Jose comes to campus and finds the garage full, what is the probability that there is a sporting event? Okay. Use a tree diagram to solve this problem, because otherwise it's going to be terrible, right? But I do want to give you just a couple of minutes to try mapping out a tree diagram and potentially solve the problem. Just to nudge you along, the event that's taking place has to be the first set of branches, right? Because the probabilities that were given is the probability of being full, given that it was an academic event, for example. Is that what the? Yes.
yeah, so.
it's not even. Very few people work. Potentially, yeah. All right, I think we're ready.
All right. So like I said, and I guess I should have paused the recording. It's a very boring, and you won't know. Until you see this. We've started again. Whoa, okay, stop. Oh, boy. It's like, okay, too much. Okay, so like we said, right, the first thing that we have is what type of event is going on. And so the event, and I'm gonna be lazy and I'm not gonna define the letters that I'm about to use because hopefully they're obvious, okay? And so okay, 3 events, and I'm gonna give myself lots of space here. 1, 2, hey, that wasn't lots of space. 3. How about like that? Okay, so the first thing I'm gonna do is map this information. Yep. So I've got academic events, I have sporting events, and no events. I also have the probabilities of these things, right? And so I know the probability of A is 0.35. The probability of sporting events is 0.20, and the probability of no events is 0.45. Okay. So then the next thing that we're going to look at, and the only reason that I set them up in this way is because this probability, so when there is an academic event, the garage fills up about 25% of the time. So then, because that's a conditional probability, the garage is either full or not full. All right. When there is an academic event, okay, so I had to head down this academic branch, and then it's either full, which is 0.25, or not full. So knowing that it's full 0.25, right, then not full is going to be 0.75, right? 1 minus 0.25. Because if there's an athletic event, right, the garage is either full or not full. There are no other options, right? And so then I have 0.75 down here. And this layer, let's call it, right? So here, let's write event. You've got kind of an event layer and the garage layer of events, I guess. Kind of confusing to have event in there, but don't know what else to summarize it as. So then we have the same scenario, whether it was a sporting event or no event, right? The garage is either full or not full. And so same idea here, full, not full, full, not full. Just to map out. So it fills up 70% of the evenings with sporting events. So 0.70, and which means it's not full, 0.30. And on evenings when there's no event, what color haven't I used? It only fills up about 5% of the time. So 0.05, you don't want to mess that up, right? 0.05 is way different than 0.5, right? And so yeah, 0.95 there. Okay. So at each level, things have to add, or for each cluster of branches, I guess, things have to add to 1, right? There's either an academic event, a sporting event, or no event. There are no other options. We're assuming that, okay? The garage is either full or not full, right? Regardless of the event. Okay. So here's the problem we want to solve. If Jose comes to campus and finds the garage full, what is the probability that there is a sporting event? Okay. So this is kind of tricky, right? Especially translating it into probability notation, okay? And so what we're gonna do is we're just kind of gonna massage this a little bit. So he came to campus and he finds the garage is full. Now, the garage is full. There are 3 different ways to have a full garage, right? And so I usually use kind of like a highlighter or something, or sometimes I put a little check mark underneath the events that make that happen, right? The garage being full. Okay. But I'll use the highlight. Okay. So these are all the possible ways that the garage could be full. Right? And so if I asked you, what's the probability that the garage is full? What would you have to do? You'd have to multiply down each branch, right? And so here you have a F, a not F, S, F, S, not F, N, F, and N, not F. Right? I've cut out the and, but then below that you can write the probabilities of A and F, right? By multiplying down each branch. And so let's see here. The probability of A and F, which I'll just use AF, is 0.35 times 0.25, which puts me at 0.0875. Pretty quickly, because it gets so tedious writing it all out. Usually what I resort to is I write out the combinations just because I find it helpful when I'm kind of looking through the combinations, okay? But then all I do is I write the probabilities underneath, right? And just by multiplying down each of the branches. Sometimes I find it helpful just to get it all out of the way, just do all the work and then look at the question and figure out what components I need. Okay? And so if you multiply down each of the branches, you would find 0.2625, 0.14, 0.06, 0.0225, and 0.4275. So one thing, right? And so just multiply down all the branches, and now I have these probabilities. Okay. Just to double check, right? It's always good to make sure that these add to 1, right? Because it's all possible outcomes. Okay. So the sum, assume the sum is 1, hopefully. I did not check, but I'm assuming. Okay. Back to the question we want to solve. If Jose comes to campus and finds the garage full, so we're given that the garage is full, what is the probability that there's a sporting event? So now going back here. So we want to find the probability of S given that the garage is full. Which means, right, if we have our conditional probability formula memorized, or rather on a formula sheet, of course, you'll have it. I was this close to bringing them today, but then I hadn't looked them over, so there might be stuff written on it from the final exam last term. And that would be very bad. So the probability of S and F divided by the probability of F. Okay. When we've broken it out like that, all of a sudden, okay, we can do this, right? Maybe. So the probability of S and F, it had to be a sporting event and the garage has to be full. That happens, the probability is 0.14, right? And so the probability of S and F is 0.14. The hard part is finding the probability of being full, right? And so here, I guess, so this here is 0.14 from the tree. Okay, that doesn't look like a tree. Yeah. But we need to find this. Okay. And there are 3 branches that result in a full garage. Right. I don't know where that's, it sounds like it's coming from like the corner. I don't know. Right, and so that's what the highlights are about, right? These 3 branches. I did that because we need it. All right, so then what we can find is we can say, okay, the probability of being full is going to be the probability of A and F. Plus the probability, where is that coming from? Plus the probability of S and F. Plus the probability of N and F. Oops. Right, A and F, or, right, and so the ands mean that you're multiplying, and so that's how we got to the end of these branches, right? Or means that you're adding across the branches. And so here, this means that you're multiplying, whereas, and maybe I should follow the same, I should write or. Otherwise, it's all discombobulated. And that's pretty funny. Right? Or now it'll match, which means you're gonna add. Do I just go for it? Yeah, 0.0875 plus 0.14 plus 0.0225. So that's the benefit of having written the probabilities at the end of each branch, because now you can just grab whatever you want and then just work with those. And I get a nice 0.25. That's a pleasant surprise. Almost makes you wonder if I did something weird. Did I?
Something different. Necessarily sure that I did it right.
0.0875. I'll just do this one first, plus 0.14 plus 0.0225. I do get 0.25. Question is, did I multiply down the branches? 0.35 times 0.25. Yes. 0.2 times 0.7. All right, good. 0.45 times, oops, not divided by, times 0.05. All right. Rocking and rolling. So now I want this. Okay, not quite so much. How can I keep this on one page? Oh, I never like to do it right across the page. It's bad. But it's the last thing I'm gonna write in chapter 3, so I don't have. Okay, fine, fine. I'll even bump this down. That's how much I could not write my equal sign across the page. I wanted to be cool, but I'm not. 0.14 divided by 0.25, right? I'm allowed to do that because I've already shown what these values are. So now I can just plug them in and we get 0.56. So Jose comes to campus, finds the garage is full. The probability that there is a sporting event, 0.56, right? Given that the garage was full. I know that it would be very tempting to tell me, oh, it's just 0.2 because that's the probability of a sporting event, but we have this knowledge that the garage is full, and so that's why it's 0.56. This doesn't look very nice. Any questions about that one? No.
Sorry, Emily. Sorry, Emily.
Hello?
Can you go for that? Hello.
Oh.
Hello.
Hello? Say that again. No? Maybe? Okay.
Like,
So-
can you go over that? Can you go over that?
Go over the last part,
Yeah. Yeah. Yeah.
starting
The formula, like a probability. The formula, like a probability of.
Oh, this one here?
Yeah. Yeah.
Okay, I've used the general formula that the probability of A given B is the probability of A and B divided by the probability of B. That's just the general conditional probability formula. So now I am going to make a note here that review sections. Yeah, 3.3, 3.4, and 3.5 on your own. Okay, not tested. I will say that. And well, I guess I blabbed my way out of time, but conditional probabilities are really hard. So it's nice to spend some time here. Yeah. No. I know, right? Yeah, I should just wait for the applause.
Yeah.
Sometimes it feels like it's coming from here and sometimes, I don't know. Yeah, weird, right? Oh. Oh, weird. We'll start 4.1 on Tuesday. You guys get a free pass. Or sorry, Thursday. Today is on Thursday. How about that? We'll start fresh. We'll end a little bit early. If you have any questions, let me know. I'll post a conditional probability assignment for you guys if I haven't already. I'll see you on Thursday. I'll stop this recording.